Hello. In this last part of the lecture, we are going to discuss the operation modes of the generators. These operation modes include the standalone and the grid-connected modes. We are going also to discuss how changes to the load or changes to the excitation voltage affect the operation of the grid-connected mode. We are also going to discuss the operating limits of asynchronous generators. So let us get started. The behavior of a synchronous generator varies greatly under load depending on the power factor of the load and on whether the generator is working alone or in parallel with other synchronous generators. Although most of the synchronous generators in the world operate as part of large power systems, we are going to start our discussion assuming that the synchronous generator works alone. So over here we can see that in the case when the generator works in the standalone mode, in this case the generator operates in isolation with a variable connected load across its terminals, and the terminal voltage is called the voltage phase and varies as the function of the load and the excitation voltage. So as these two changes, this will cause the voltage per phase to change. In a grid-connected mode, on the other hand, the generator connects to a network of large generators, and in this case, the phase voltage is kept fixed. Let us take a look on the case when there is an increase in the load with no change on the excitation voltage. What will happen is that an increase in the load is an increase in the real or reactive power drawn from the generator. And since the field resistor is unaffected, the field current is constant and therefore the flux is constant too. Since the speed is assumed as constant, the magnitude of the internal generated voltage is constant also. Now, assuming the same power factor of the load, change in the load will change the magnitude of the phase current. However, the angle will stay the same, and this is because of constant power factor. So the armature, the reaction voltage or the phase voltage will be larger for the increased load. So we can see here that the phase voltage in the second case is increased. And since the magnitude of the internal generated voltage is constant, the voltage, the phase voltage, will move parallel to its initial position. Generally, when a load on a synchronous generator is added, the following changes can be observed. First, for lagging loads, the phase voltage decreases significantly. Second, for unity power factor, this means that we have a purely resistive load, the phase voltage decreases slightly. And the last case, for leading or capacitive load, the phase voltage rises. In all cases, this will cause a change in the load angle as observed over here. Now, let us take a look at an example which is related to the standalone mode. Imagine that there is a star-connected 398 volt phase RMS and 25 kilovolt ampere rated standalone micro-hydro three-phase synchronous generator is operating near Galway in Ireland. It has a synchronous reactance of 3.5 ohm. Considering an operating point of 18 kilowatt at rated current with a lagging power factor and rated terminal voltage, calculate the following parameters. So we want to calculate the phase current, the reactive power, the power factor, the required excitation voltage, and the load angle. Also sketch a phasor diagram indicating the identified parameters. The first value we want to calculate is the phase current. We are already given in the question the apparent power, which is over here, and we know that from its unit. So since we have the apparent power, We also have the phase voltage. We can get the phase current by this formula. So the equation for the apparent power is this. If we plug in all the known parameters, we will get the phase current. And this ends the solution for the first part. Now the next parameter we want to calculate is the reactive power. Now think carefully, how can we make use of the given parameters in order to calculate the reactive power? We already have the real power, we have the apparent power. So having these two information, this will help us calculate the power factor over here. So remember that the power factor is the real power over the apparent power, and having this value will give us the angle phi, which if we plug over here in the formula of the reactive power will give us the value of the reactive power. So always notice that you have to include the unit in your answer. So this way the reactive power is calculated. The next parameter they want us to calculate is the power factor, which we have already done over here. So this is the power factor. So let's move on to the fourth requirement, which is the excitation voltage. Now notice that in order to calculate the excitation voltage, we need to sum the phase voltage and the voltage drop across XS, or the inductance reactance. So we already have got the phase voltage given in the question. What we need to calculate is V dropped across XS. So we are given X of S, and we have already calculated the current. If we plug them here, we will get the voltage drop across the inductance reactance as this value. So this is the magnitude and the phase. If we put these values in the equation of the excitation voltage, do the phasor sum, we will end up with the magnitude for the excitation voltage and this angle, which is the load angle. So this is the last parameter they want us to calculate, that is the load angle. And if you draw a phasor diagram for all the given or the calculated parameters, it will look something like that. Now let's take a look at what happens in the grid connected mode. Remember that for a constant power line, it is also valid in the standard phasor diagram, because the parameter 3 times V phase square over X is a constant. Because remember that for a grid connected mode, the terminal voltage is fixed. So the power, which is constant, is indicated by here. So this is the real power. This is the amount of the power. So this line over here, it shows us the constant power line. And if we actually take the value of the product of multiplying the current phase by the power factor, we will also get this will indicate the power. So this is the magnitude of the power, and here, if we extend it, it will hit here. And in order to understand its vertical amount, it would be actually indicated by the length of the product of these parameters. So to understand this better, let us take a look at this question. So determine the changes to the phasor diagram for a 2 times increase in the output power and no change in the excitation voltage. So we want to do that only on the phasor diagram without any calculations initially. We need to note that the phasor, the per phase voltage is kept fixed, but we will change only the power. So assuming that the real power is over here, so this is the starting point. Okay, now in order to understand what is the length of that power on this axis, this is the power axis, let's say. Okay, so this is P1, and the amount of it is determined by the component I phase times cosine theta. So we will have this much as the first P. So this is P, the initial P. Now we want to double P. So we extend this to double. So you can use a ruler to do that. We do that horizontally and we do that vertically. Okay? Why we are doing this? Because we want to know what is the new change in the phase diagram. Next, what is done is that once we have the second power, okay, so this is the vertical new line for the doubled power, and this is the new horizontal line for the doubled power. This will help us know the new excitation voltage by rotating the excitation voltage from this point all the way to here, and then draw the new line for the excitation voltage. Now the vertical power line will help us know the new phase current. So the new phase current will be rotated from here or extended from here to there. So now we have the new phasor diagram for doubling the power. Now, also notice in the second case that it is possible to change the excitation voltage without changing the power or the output power. So this can be evident from this phasor diagram, where the phase voltage is decreased from here, okay, let me take the pen, to over here. However, the power is kept constant at the same line. And in this case also, the voltage, the phase voltage is kept fixed. However, a change in the excitation voltage will do a change in the current. So the current will change from here to over here. Now let's take a look at some of the operational limits of a grid-connected mode generator. The first limit is that the generated power is always less than the input power. And the input power is determined by the prime mover, which could be a wind turbine, a gas turbine, a water turbine. Okay, now we can see that if we assume that the phase voltage remains constant through the grid connection operation, and that the inductive reactance remains constant also through the operation, the power cannot go beyond the input power. So this means that the generated power cannot go beyond the input power. The next limiting factor is the stator copper loss, which is determined by this parameter over here. So if there was a loss, this implies a limit on the produced phasor current, and this will cause a limitation on the operation of the generator. Another limiting factor is the rotor copper losses, which is also affects the excitation voltage. And this happens when a magnetic saturation of the stator and the rotor is reached, and this would limit the current, the DC current that is connected to the rotor winding and the produced voltage. And due to these losses, there would be a problem on the operation of a grid-connected mode. Due to these limitations, there will be a maximum excitation voltage that can be obtained and a maximum power that can be delivered. So the operation of the generator is always kept inside these two circles in order to produce a maximum current or a maximum power. So a good operating strategy could be by controlling the excitation voltage according to the power demand. So basically operate with as low a value of the excitation voltage as possible, and this can be controlled by the DC current which is fed to the rotor winding. And in this case, it is kept to a minimum value, and without the load angle reaching to 90. So always, in this case, the load angle is kept to a maximum value, and that's to ensure a stability margin is obtained for the operation of the generator. And this concludes the lecture. And at the end of this lecture, I would really like to thank you for joining us in this course. It has been an exceptional semester. I hope you enjoy it. I hope that you got an understanding of how power systems work. And I hope this inspires you to continue in that direction. I really wish you all the best and wish you good luck in your coming examination. Bye.